The cutting plane method was introduced by Danzig, Fulkerson, and Johnson in 1954. In amazing work, they found by hand a shortest possible tour through 49 cities in the United States. Even today, you can regularly see articles reporting that such a task is impossible for the world's fastest supercomputers. The argument is that there are far too many tours to be able to check them all one by one. It is indeed true that the number of tours grows very quickly as the number of cities increases. For n cities, after designating a starting point we have n-1 choices for the first city to visit, n-2 choices for the second city, and so on down to 1. The product of these numbers is called n-1 factorial. To obtain the number of tours we divide the product by 2, since we do not distinguish between a tour and its reverse order. It is no problem to list all of these tours if the number of cities is small. But such a brute force approach to the TSP is out of the question for 50 points. This does not mean, however, that we cannot solve a 50-city problem, only that we necessarily need a more subtle method. Consider, for example, the problem of sorting 50 blocks by their height. There are 50 factorial ways to order the 50 blocks. That is 100 times greater than the number of tours through 50 points. But sorting is an easy problem, having a number of algorithms that will run quickly on even a very large data set. The method we describe is not one of the most efficient, but it is very simple, and gets the job done. We will repeatedly look for a pair of blocks that are out of place, that is, the taller block comes before the smaller block in the current ordering. We then swap the positions of the out-of-place pair. Repeating this process 50 times, we obtain the following ordering. After 150 swaps we are clearly making progress. Finally, after 252 swaps, we have the blocks completely sorted. The success of this swapping sort is driven by 3 simple properties. First, we have a well-defined notion of a flaw in a candidate solution, that is, a pair of blocks that are out of place. Second, we have a way to correct a flaw, by swapping the positions of the blocks. Third, we can readily verify that a candidate solution is a correct sorting of the blocks. Can we carry out a similar solution process for the traveling salesman problem? A great difficulty is to devise a technique for step 3, that is, a way to know for certain that we have a shortest possible tour. Danzig's team handled this in brilliant fashion. Instead of working directly with tours, they repeatedly solve a relaxed version of the problem, permitting the salesman to use fractions of roads, sending half of his or herself one way, and half the other. In the middle of the process, their fractional solutions are not routes you could actually drive or walk, but by gradually correcting more and more flaws in the solutions, they zero in on a proper tour. And once they have it, they know it is the shortest possible route. Here is an outline of the process. The use of fractional tours may come as a surprise, since this increases greatly the number of candidate solutions to consider. We already had a huge haystack of tours, but rather than make it smaller, we instead add many fractional solutions to create a much larger haystack. The sequence of converging fractional solutions gives you a feeling for the overall process. But to understand the mathematics we will need to cover several important details. Just what do we mean by a fractional tour? What type of flaws will we look for? How do we adjust the fractional tour to avoid any flaws we find? And, most importantly, how do we know for sure that the final solution is the shortest possible tour? Answers to all 4 of these questions are hinted at in a spot-on summary in the news article from 1954. The writer states that the USA tour was found, quote, by an ingenious application of linear programming, a mathematical tool used to solve production scheduling problems, unquote. The general linear programming model was invented by George Dantzig. Its development was one of the great accomplishments of applied mathematics in the past century. Indeed, Dantzig's simplex algorithm for solving linear programming models was called one of the most successful algorithms of all time, in terms of widespread use. Our discussion will focus on the TSP, but it will give you a quick glimpse of the general theory of linear programming, or LP, for short. Let's begin with fractional tours. In the TSP, the task is to find the shortest way to visit all of the points and return home. We usually think of this as an itinerary, listing the points one after the other. But we can also view a tour as selecting which edges we use, where an edge is the direct link from one city to another. In a TSP with 6 cities, we have to select 6 edges that together form the optimal tour. So for each edge we have to make a choice. Do we use the edge or not? Yes or no? We can represent the decision for each edge as a variable, set to 1 if we use the edge, and set to 0 if not. For a 6-city TSP we have 15 such edge variables, 1 for each city-to-city pair. A tour is represented by setting to 1 each of the 6 variables for edges that are used in the tour, and setting the other 9 variables to 0. For such a representation, the length of the tour can be computed by adding together the product of the length of each edge, times its corresponding edge variable. This expression of the tour length is a linear function of the variables. In general, a linear function is obtained by multiplying each variable by a number and summing the products. So, the TSP can be described as minimizing the linear function of the edge variables, subject to the condition that they take on 0 or 1 values that together represent a tour. Dantzig's team did not know how to directly solve this model, so, in true mathematical fashion, they worked instead with a model that they did know how to solve. They would attack the TSP with linear programming. In this research, they followed the pioneering work of Julia Robinson, who first proposed, in 1949, to use Dantzig's tool of linear programming to study the salesman problem. The linear form of the distance function was perfect for her plan. This is precisely the type of function that Dantzig requires in his general LP model. But the constraint that requires the edge variables to represent a tour would have to be relaxed greatly. Firstly, LP models can have only constraints that can be expressed as linear equations or linear inequalities. The specific statement that the variable should specify a TSP tour is definitely not of this form. Secondly, LP models must allow variables to take of fractional values. We cannot require the edge variables to be only 0 or 1. Robinson simply made do with the types of constraints that Dantzig's model allowed. Rather than working with zeros and ones, she let the edge variables take on any fractional values greater than or equal to 0. She also required that for each city, the edge variables meeting that city must sum to exactly 2. This is a property shared by all proper tours, since the salesman must arrive at the city by one edge and leave the city by a second edge. The candidate solutions to the LP model are what we are calling fractional tours. Here is an example of such a solution for a 6-city problem. The red edges are assigned the value 1/2, and the black edges are assigned the value 1. You see that each city meets 2 red edges and 1 black edge, so the sum of the values is 2, as Robinson required. Robinson's LP will not by itself solve the TSP, but it is the starting point of the breakthrough work by Dantzig's team. Their cutting plane method will repeatedly look for flaws in the optimal fractional tour. To see what we mean by this, it is best to consider an example of an optimal solution to the initial LP. But be warned, you are not going to like the solution. Here is the optimal fractional tour for the geometric version of the 49-city USA problem. This satisfies the constraints of the LP model. Each city meets exactly 2 black edges. But to save distance, the sneaky salesman just went back and forth between many pairs of cities. That is, she assigned to many edges the value 2. These doubled edges are flaws that Danzig's team can address with additional LP constraints. But, before we consider this, let's discuss how we know that the displayed fractional tour is the shortest possible solution to the model. Of course, we could simply rely on the fact that the simplex algorithm is designed to produce optimal solutions, but there is a much nicer way to convince ourselves that we have the shortest fractional tour. Indeed, we do not need to trust that Bob Bixby or another superstar computer coder has correctly implemented the simplex algorithm. Not that Bob is untrustworthy, I'm just saying. Suppose we draw a disk, centered at one of our cities, say, Boise, Idaho. We call this a control zone. Any TSP tour must use 2 edges meeting Boise, so every tour must cross the control zone at least twice. This means that every tour must have length at least twice the radius of the zone. It is useful information, since we now have a lower bound on the length of any TSP tour. In fact, twice the radius of the zone is also a lower bound on the length of any fractional tour, since the sum of the edge variables meeting Boise must be 2. Again, this is useful information. Now suppose we create a second control zone, around Minneapolis. Since the zones do not overlap, we know that every tour, and fractional tour, must have length at least twice the sum of the radii of the 2 zones. In this bounding game, bigger is better. Twice the sum of the 2 radii is a better bound than looking at Boise alone. So let's go all in, creating a control zone for every city. Some of the zones have radius 0, and others are too small to see in the figure, but none of them overlap. Therefore, no tour can have length less than twice the sum of the radii. Notice that our fractional tour crosses each zone exactly twice, and that the zone covers completely all edges in our fractional tour. This means the length of the tour is exactly the same as twice the sum of the radii of the zones, and thus matches our lower bound. We can conclude that we do indeed have a shortest possible fractional tour, since no fractional tour can have length less than the bound. This is not an accident. The best packing of control zones is the one that gives the greatest lower bound. Now, no zone lower bound can be greater than the length of our fractional tour. So, we can also conclude that we have the best possible packing of zones. The zones show that we cannot obtain a better fractional tour, and the fractional tour shows that we cannot obtain a better packing of control zones. Together, it means that both the tour and the packing are optimal. It is a fantastic theorem that such an equality between the minimum tour length and maximum zone bound is always true, for any collection of points you can draw. Let's look at this in more detail. Finding the best packing of control zones is itself a linear programming problem. We have a variable for each city, where the value of the variable is the radius of the control zone for the city. To obtain the best bound, we maximize twice the sum of the variables. But we must be sure that the zones do not overlap. So, for each pair of cities I and j, we have the constraint that the sum of the 2 radii can be at most the travel distance between I and j. This zone packing LP is designed to produce a lower bound on the length of any solution to the fractional tour LP. The pair of problems are partners. In linear programming terminology, the fractional tour LP is called the primal problem, and the zone packing LP is called the dual problem. It is a general feature of linear programming that every LP has a corresponding dual model. A crucial feature is that, for any candidate solution to an LP model, its length cannot be less than the bound given by any candidate solution to its dual model. This is known as the weak duality theorem. It seems a pity to call such an important property a weak theorem, but the name strong is reserved for a different result, first proved by John von Neumann. The strong duality theorem states that, if we have the best possible solution to the primal LP, and the best possible solution to the dual LP, then the primal length will be exactly equal to the dual bound. This is great. If we have both the primal and dual solutions for our problem, then, by checking that the length equals the bound, we know that for this pair, at least, the computer code delivered the correct results. Both the primal and dual solutions are optimal. Returning to the TSP, we use LP duality to certify that we have an optimal fractional tour. For geometric data, this can be visualized with the drawing of control zones, but also for non-geometric data, LP duality provides a guarantee that we have the shortest possible fractional tour. Every TSP tour satisfies all of the constraints of the fractional tour problem, so we also know that no TSP tour can have length better than the dual LP bound. This is the heart of the TSP cutting plane method. If we reach a fractional LP model that has a TSP tour as an optimal solution, then we know that we have solved the salesman problem. We have a shortest possible tour. If anyone asks you how is it possible to solve a TSP without checking, one by one, every possible tour, you can answer with 3 short words: linear, programming, duality. We now have the pieces in place to describe the TSP cutting plane method, adopting the 3 major steps of the simple sorting algorithm we described earlier. At each stage we have a fractional TSP tour. Flaws are identified by linear inequalities that are satisfied by all proper tours, but violated by the fractional tour. We correct each flaw by adding the violated inequality to the LP model, and computing a new solution with the simplex algorithm. If we reach an LP that has a proper tour as an optimal solution, then we verify optimality using the LP dual solution. With the solution verified, we have solved the TSP. It is as easy as 1, 2, 3. Let's see how this works in practice. Here again is the optimal fractional tour and zone packing for the 49-city USA problem. The solution contains many isolated pairs of points. Each of these 2-point subtours is a flaw. The corresponding TSP inequality states that the edge variables leaving the pair of points must sum to at least 2, since a proper tour would need to enter and depart the 2-point island at least 1 time. Adding these constraints, and solving with the simplex algorithm, we obtain the following fractional tour and dual solution. The gray objects that look like figure 8s represent the new dual variables, corresponding to the each 2-point constraint. A proper tour must pass at least twice through each figure 8 region, so we can add twice the width of each region to our TSP lower bound. This gives a better dual bound than what we had obtained using control zones only. We are making progress, so let's continue with the process. There are no longer any back and forth subtours in the solution, but it still has the obvious flaw that the fractional tour is not connected. The 2 connected components of the solution are indicated by the red and yellow points in the drawing. This flaw can be corrected by adding an inequality, stating that the edge variables leaving the yellow set of points must sum to at least 2, since, again, a proper tour would need to enter and depart the yellow set at least 1 time. Such TSP inequalities are called subtour elimination constraints. In general, violated TSP inequalities are called cutting planes, since they cut off the flawed fractional solution. Here is the new fractional tour. The purple object represents the dual variable corresponding to the subtour elimination constraint. The object surrounds the nodes that were colored yellow in the previous figure. We know that any proper tour must cross the purple strip at least twice, so we can add twice the width of the strip to the TSP lower bound. This new dual object is called a mode, by Mike Jr. and Bill Pullyblank, who first introduced the use of geometry to represent the TSP dual solution. The fractional tour is now connected, but there remain subtour elimination flaws in the solution. For example, consider the set of 4 nodes highlighted by magenta. The sum of the edge variables entering this set is only 0.67, so the corresponding subtour elimination constraint is violated by 1.33. Such subtour cutting planes can be found efficiently, using algorithms from network flow theory. Adding 9 such violated subtour constraints to the LP model, we obtain the following new fractional tour and dual bound. The new solution is not connected, so we can again add a subtour constraint for one of the two connected components. Let us now go quickly through several steps of the algorithm. After adding the constraints and solving the LP, the new solution, again, has two components. There is now a single component, but we identified 4 violated subtour constraints for the solution. Oops, we are now back to a 2-component solution. The problem is stubborn. We again have a 2-component solution. Yes. Connected. But with 2 violated subtour constraints. We are not quite home. The LP now produced a 3-component solution. Connected again, but the solution has 2 violated subtour constraints. Finally, the fractional tour satisfies all subtour elimination constraints. But that is not the end of the line for the cutting plane method. An old theorem of Minkowski, from convex geometry, tells us that if the fractional solution is not a proper tour, then there always exists a cutting plane. The difficulty is to efficiently identify the flaw in the fractional tour, together with a TSP inequality to correct the flaw. Let's look more closely at the current fractional tour. It is easier to see the structure without the drawing of the dual bound. The points highlighted by magenta form a red triangle, joined to the remainder of the solution by 3 black edges. These 6 edges, 3 red and 3 black, have edge variables that sum to 4.5. But no proper tour can include more than 4 of these 6 edges. So we have identified a flaw in the fractional solution. The corresponding TSP inequality is called a blossom constraint. There is also a second violated blossom constraint, formed by the red circuit of length 7, just below the highlighted triangle. Adding these 2 blossom constraints, and solving again the LP model, we arrive at the following fractional solution. There is no geometric representation of the dual LP bound, when we have blossom constraints in the model. But we still have LP duality to prove that the displayed solution is an optimal fractional tour. There are no violated subtour or blossom constraints for this solution. But it is obviously not a proper TSP tour. Indeed, the Concorde code identifies several more general TSP constraints, called comb inequalities, that are violated by the fractional tour. Let's add these as cutting planes to our LP model. Goody. The optimal solution to the fractional LP model is a proper tour. Together with the tour, we also have the dual LP solution, giving a short mathematical proof that our result is the shortest possible tour for the 49-city problem. Goody goody. That is it. To see the cutting plane method in action, you can download the free Concorde TSP app from the Apple Store. For more information on the TSP cutting plane method, please have a look at chapters 5 and 6 of the book, In Pursuit of the Traveling Salesman. Thank you.